14th International Physics Olympiad Year 1983 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. My Skype name is Eduard F. 1996. Problem 3. Prisms, 7 points. Two dispersive prisms having apex angles A1 equals 60 degrees and A2 equal 30 degrees are glued as in the figure below. Angle C equal 90 degrees. The dependencies of refraction indexes of the prisms on the wavelength are given by the relations n1 and n2, where A1 equal 1.1, B1 equal 10 power 5 square nanometers. A2 equal 1.3, and B2 equal 5 by 10 power 4 square nanometers. Question A. Determine the wavelength lambda 0 of the incident radiation that passed through the prisms without refraction on AC face at any incident angle. Determine the corresponding refraction indexes of the prisms. Question B. Draw the ray path in the system of prisms for three different radiations lambda red, lambda 0, lambda violet, incident on the system at the same angle. Question C. Determine the minimum deviation angle in the system for a ray having the wavelength lambda 0. Question D. Calculate the wavelength of the ray that penetrates and exits the system along directions parallel to DC. Question A. Determine the wavelength lambda 0 of the incident radiation that passed through the prisms without refraction on AC face at any incident angle. Determine the corresponding refraction indexes of the prisms. Solution. The ray with the wavelength lambda 0 passed through the prism system without refraction on AC face at any angle of incidence if n1 of lambda 0 equal n2 of lambda 0. Relation 3.1. From here we have relation 3.2. The wavelength lambda 0 has correspondingly the form 3.3. Substituting the furnished numerical values lambda 0 is 500 nanometers. The corresponding common value of indexes of refraction of prisms for the radiation with the wavelength lambda 0 is 1.5. The relations 3.4 and 3.5 represent the answers of question A. Question B. Draw the ray path in the system of prisms for three different radiations lambda red, lambda 0, lambda violet, incident on the system at the same angle. Solution. For the rays with different wavelength having the same incidence angle on first prism, the paths are illustrated in the figure 1.1, since for the wavelength lambda 0 equal to 500 nanometers both refractive indices are equal to 1.5, the angle of refraction on the first face AD will be less than the angle of incidence according to the Snell's formula. Then the second face array will pass without deflection, as shown in the figure. Next, since n1 lambda red is less than n1 lambda 0, on the first face AD the red ray will go above the 0 ray. And further, since n1 lambda red is less than n2 lambda red, the red ray will deviate upward after refraction at the boundary AC. And it will deviate even more at the boundary with air. The violet ray behaves the opposite way. Since now n1 lambda violet is greater than n1 lambda 0, on the first face AD the violet ray will go below the 0 ray. And further, since n1 lambda violet is greater than n2 lambda violet, the violet ray will be deflected downwards after refraction at the AC boundary. And it will be deflected even more at the BC boundary with air. So the draw illustrated in the figure 1.1 represents the answer of question B. Question C. Determine the minimum angle of deflection in the system for a beam with a wavelength of lambda 0. Solution. Let's complete our prisms to a triangular one with an upper angle A' equal to 30 degrees. For a wavelength of lambda 0, we have n1 lambda 0 equals n2 lambda 0 equals n equals 1.5. Let's mark the angles I1, I2, J1 and J2 in the figure. Then, from Snell's law of refraction of rays, we have the following two relationships. In general, the angles I and the angles J are not equal to each other. But in this case, when the angle I1 changes in one direction, the total angle of deflection will decrease, and in the other direction, it will increase. That is, at different angles the minimum is not observed. It can only occur if I1 is equal to I2, and J1 is equal to J2. But in this case, J1 is equal to J2 is equal to the angle A' in half. From the figure it is clear that the total angle of deviation will be equal to I1 plus I2 minus A', which as a result of all the numerical substitutions gives the angle of deviation equal to 15.7 degrees. This is the solution to the question of C. Question D. Calculate the wavelength of the ray that penetrates and exits the system along directions parallel to DC. Solution. Using the figure, the refraction law on the AD face is 3.11, the refraction law on the AC face is 3.12, as it can be seen in the figure, and I1 equal 30 degrees. Also R1 plus R1' equal A1, substituting 3.13 and 3.15 in 3.12 it results 3.16, or 3.17, because of 3.11 and 3.15 it results that 3.18 and 3.19, putting together the last three relations it results 3.20. Because angle A1 is 60 degrees and angle 2 is 30 degrees, relation 3.21 can be written as this expression. Or as expression 3.22, considering the relation's numeric values for n1 and n2 and operating all calculus it results quadratic equation 3.23 to lambda square, solving it one determine the wavelength lambda of the ray that enter the prism system, having the direction parallel with DC and emerges the prism system having the direction again parallel with DC. That is lambda equal about 1.2 micrometers. This represents the answer of question D.